All right. Thank you, Joe. So it's my great pleasure to introduce Dr. Mei-Sing Ong. Dr. Ong is an assistant professor at Harvard Medical School in the Department of Population Medicine at Harvard Pilgrim Healthcare Institute and affiliated faculty in the Computational Health Informatics program at Boston Children's Hospital. She's also the director of clinical informatics for the New England Immunodeficiency Consortium. She trained originally as a computer and biomedical engineer, then earned her PhD in health informatics at the University of New South Wales in Sydney, her hometown, where she's joining us today, 10:30 p.m. there. She continued her work in health informatics through several years of postdoctoral training in Sydney, Boston, and at the National Center for Advancing Translational Sciences, NCATS. Her work is currently supported by an R01 focused on improving diagnoses of primary immunodeficiencies among patients from racial and ethnic minority backgrounds, PCORI funding to use machine learning to predict disease trajectories in relapsing and remitting diseases, and several other awards. I met Dr. Ong at a recent pediatric rheumatology conference where she gave an eloquent and thought-provoking talk on the same topic she'll discuss with us today, artificial intelligence in medicine. I was thrilled that she accepted our invitation to present Grand Rounds, and I know you'll enjoy her presentation. So take it away, Dr. Ong.
Thanks very much for the introduction, Dr. Binder, and thank you for the invitation to speak. I'm very pleased to be here. Just a very quick disclosure, I received funding from Pfizer through an investigator-initiated grant with no direct relation to the work I'm presenting here today. So, as you know, there has been an enormous surge of interest in AI in recent months, driven primarily by the success of ChatGPT. AI has been trumpeted as the next big technological revolution, comparable with the advent of electricity and the internet. And investment in AI has also skyrocketed across many different industries that are not traditionally tied to AI, including healthcare. So along with the growing interest in AI, there is also a growing concern about its potential harms. There are fears that AI could be used at scale to spread information, misinformation and propaganda, or that it could eliminate millions of white-collar jobs. And recently, a group of industry leaders warned that AI might one day pose an existential threat to humanity. And among those who signed the statement were pioneers in the field of AI. The UN Secretary General stated recently that mitigating the risk of extinction from AI should be a global priority alongside pandemics and nuclear war. And more people are concerned that AI will replace doctors one day. So is AI really going to take over the world and our jobs? Or is this inflated hype? How should healthcare providers respond to the growing use of AI in medicine? And what are the opportunities and risks of AI in medicine? So my goal today is to provide you with some foundational knowledge that can hopefully help you answer some of these questions. I'll first give a very high-level overview of AI and machine learning. I will then review some published works on the application of AI in medicine. I will also briefly describe the barriers to the adoption of AI in medicine, and finally, the threats of AI. So first of all, what is AI? It is the capacity of a machine to perform tasks that mimic human behavior, including problem solving and learning. So AI is virtually omnipresent these days. It's telling us where to go, what to read, and it's helping us with our daily tasks. So AI started with Alan Turing, who was the founding father of computer science. Turing was a British mathematician responsible for breaking the Nazi Enigma code during World War II. His work played a major role in helping the Allies win the war in Europe and also laid the groundwork for modern computer science. Turing proposed what is known as the Turing test as a criterion for whether a computer is thinking. So the Turing test states that if a computer can fool someone into thinking it is human, then it has achieved human-level intelligence. The test proposed by Turing involves having a human interrogator speaking with a human and a computer through a computer terminal. And the interrogator has to decide which terminal is operated by a human and which is operated by a computer. Turing test has remained the standard by which artificial intelligence is measured. So the very first computer to pass the Turing test was a chatbot named Eugene Guzman. It is an AI chatbot, which is a computer program designed to simulate conversations with human users. Eugene posed as a teenager from Ukraine who likes hamburgers and candies. And in 2014, Eugene managed to fool 33% of people who chatted with him in a 5-minute keyboard conversation. The benchmark is set to 30%. This achievement was marked as a milestone in computer science. So in late 2022, the advent of ChatGPT reignited conversation about the likelihood that the Turing test has been met. ChatGPT is also a chatbot. A recent study tested ChatGPT on the US medical licensing exam and found that the program performed at or near the passing threshold for all written exams without any specialized training, which is quite impressive. So AI and machine learning are often used interchangeably, but machine learning is actually a subfield of AI. Arthur Samuel, who was a pioneer in machine learning, defined it as field of study that gives computers the ability to learn without being explicitly programmed. So we can think of machine learning as algorithms that automatically learn insights and recognize pattern from data and gets better at it with practice or with more training data. So it's important to understand differences between machine learning and statistics so we know when to apply machine learning versus statistics. A major difference is in its purpose. Statistical models are designed to draw population inferences from a sample. This is done through fitting of a probability model. Machine learning models, on the other hand, are designed to find generalizable predictive patterns. This is done through learning a mathematical function that best describes the data. So another difference is the assumptions made about the data. Statistical models typically require some knowledge of the population. For example, we need to know whether the data are normally distributed, whether two variables are linearly correlated. Machine learning does not typically make any assumptions about the data and can be effective even in the presence of complicated nonlinear interactions. Another difference is that statistical models are designed for low-dimensional data, whereas machine learning is designed for high-dimensional data. So which is better? The answer is it really depends on the research question. Statistical models allow us to make inferences, and machine learning allows us to make predictions. Both inferences and predictions can be of value. For example, we use statistics when we want to know if drug A is more efficacious than drug B. And we use machine learning when we want to predict how a patient will respond to drug A. Another example, in genetic studies, we use statistics when we want to know if certain genes are associated with a disease. We use machine learning when we want to predict the presence of a disease based on a set of genes. So machine learning is particularly useful in situations where human expertise does not exist and when humans can't explain the expertise. It is also especially useful for learning from complex, huge amounts of data and when a system needs to adapt to a changing environment. So here are some classic examples of tasks requiring machine learning. These include facial recognition and handwritten digit recognition. So these tasks are very easy for our human brain, but it's extremely difficult to manually program the correct behavior. For example, we all write differently, and it's difficult to explain what makes 2 a 2 or what makes 5 a 5. These tasks can be easily learned by a machine learning model. So there are 3 major classes of machine learning algorithms: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning learns a function that maps a set of inputs to the desired outputs. We use supervised learning when we want to predict an outcome. Unsupervised learning looks for patterns in data. For example, we use unsupervised learning to identify natural clusters in data. Reinforcement learning is a learning system that interacts with the world by trial and error and is capable of learning by mistakes. So there are many different algorithms under each of these classes of machine learning, which I will not have time to go into. But I will quickly touch on one particular class of algorithms known as artificial neural nets and deep learning. So these are the most talked about methods and arguably the most powerful. Most modern AI applications use this technology, including ChatGPT and self-driving cars. Artificial neural nets and deep learning are a subfield of machine learning, modeled to mimic the way a human brain works. The goal is to learn an unknown mathematical function by experience. So the basic building block of a neural net is known as perceptron, which mimics the function of a neuron. And the neural net is composed of many perceptrons linked together, as shown in figure D here. When we train a neural net, the network adjusts its internal structure, and with more training data, the network becomes better at approximating the desired function. So this is similar to synaptic pruning in the brain. Deep learning uses multi-layered neural nets to learn representation of data with multiple levels of abstraction. Each layer transforms input data into increasingly more abstract representations, and with enough layers, very complex functions can be learned. So in the next few slides, I will talk about an emerging subfield of AI known as generative AI. So these are AI models that are capable of creating new content, such as text generation, image creation, and video generation. The goal of a generative AI model is to learn the patterns and relationships in a data set, and then use the learned patterns to generate new content. Most generative AI models are constructed using neural nets and deep learning. So here is an example of a generative AI model capable of generating realistic images. All the photos shown here are images of people who do not exist. And if you're wondering why they all look like celebrities, it's because the algorithm was trained using photos of celebrity. So here is another example. This is a face aging predictive model. Given a photo of a person, the model is capable of predicting how the person's face might age over time. So generative AI has also been used successfully for text-to-image synthesis. Given a textual description, the AI technology can generate an image described in the text. For example, the lower right image here was generated by the text, a hot air balloon in shape of a heart, Grand Canyon. So recently, generative AI has been successfully used to generate written human language. These models are known as large language models, or LLMs, and they form the backbone of ChatGPT and other chatbots. LLMs have achieved great success in a broad range of tasks, including generation of natural language text, translation of texts between languages, sentiment analysis, question answering, automated summarization, and content creation. ChatGPT is, of course, the current frontrunner in the field. So the capability of ChatGPT in creating original content is really quite impressive. I asked ChatGPT to write a haiku about mothers, and here's the response. Guiding hands so warm, love's embrace through joy and storm, mother's heart of form. Not bad for an AI model. So here's another example. I asked ChatGPT to write a short poem about the life of a pediatrician, and this is what it came up with. In a world where innocence resides, the healer steps with gentle strides. A pediatrician steadfast and true, guiding the young with care anew, which is again pretty impressive. It's not so great at creating new jokes though. I asked ChatGPT to tell me a joke about pediatricians, and here's the response. Why did the pediatrician always carry a red pen? Because they wanted to draw blood, but only on paper. I personally don't find it that funny. So how does ChatGPT work? What's inside ChatGPT? ChatGPT is basically a giant neural net with hundreds of billions of parameters. Whenever ChatGPT does something, what it's essentially doing is asking over and over again, given the text so far, what should the next word be? So how does one choose the next word? A traditional language model predicts the next word based on the probability of its occurrence in the training corpus. Let's say we've got the text. The best thing about AI is its ability we want to predict the next word. Imagine scanning billions of pages of human written text and finding all instances of this text, then seeing what word comes next, what fraction of the time. The model can then choose the highest ranked word, which in this case is learn. So to generate text, the model repeats this process again and again, predicting one word at a time. So in other words, language models are built on the theory of probability. What is the problem with this approach? Why do we need to build a neural net model? And why do we need a machine learning model at all? So there are 54 cards in a deck. Suppose each card represents a different word. How many ways can we put these 50 words together? The answer is 52 factorial, which is a huge number. This means that every time you shuffle a deck of cards, chances are that you make history. And there are more than 171,000 words in the Oxford English Dictionary. So applying probability theory alone will not be enough. This is where machine learning comes in. A machine learning model allows us to estimate the probabilities with which sequences of words could occur, even when we've never explicitly seen those sequences in a training corpus. This is what large language models such as ChatGPT are developed to do. So a key feature that is crucial to the success of ChatGPT is that it doesn't look at literal text. Instead, it looks for words that, in a sense, match a meaning. To do that, ChatGPT maps words in an embedding space to capture their context and meaning. For example, here we have an embedding space that maps words based on their sex, verb tense, and country capital. And words that are similar are positioned close together in this embedding space. So here, words are plotted in a three-dimensional space, but embeddings can have hundreds or thousands of dimensions, too many for humans to visualize. So embeddings effectively allow ChatGPT to predict the next word based on the context and meaning of text, and they play a crucial role in the success of ChatGPT and other LLMs. Another feature unique to ChatGPT is the temperature parameter. This parameter controls how much the model should take into account low probability words when generating the next word. So rather than choosing the highest rank word all the time, ChatGPT will sometimes choose a lower probability word randomly. This gives ChatGPT room to be creative and more diverse. So if you ask ChatGPT the same question multiple times, you're likely to get slightly different responses. The temperature parameter can be changed by the user. Higher values result in more diverse and creative output, while lower values make the responses more deterministic and focused. The default is set to 0.7, which is at the higher end. So ChatGPT is unquestionably an amazing technology, but there are a few important points to keep in mind when using LLMs such as ChatGPT. It's important to remember that LLMs are trained to predict the probability of a word in a given context. It has no true understanding of questions being asked, and so the responses are not always factual or logically consistent. Also, the responses generated by LLMs can vary based on small changes in input phrasing, which can sometimes lead to contradictory answers. This means that you should always double-check anything ChatGPT tells you. Another important point is LLMs are trained on data only up to a cutoff date and may not be aware of events that occurred after that point. ChatGPT's knowledge cutoff date is September 2021. It is not aware of events that happened after that. So if you ask ChatGPT who the current Prime Minister of UK is, it wouldn't know. So here's the response it gave. As of my last knowledge update in September 2021, the Prime Minister of the United Kingdom was Boris Johnson. However, please note that this information might have changed since then. So why does ChatGPT work so well? The answer is we really don't know. It is a surprise that a neural net with just 175 billion weights can make a reasonable model of human language. What we know is that ChatGPT and other generative AI technologies have made it possible for users without specialized AI knowledge to use AI technology. As Andre Karpathy, who was the director of AI at Tesla and OpenAI, said, the hottest new programming language is English. We no longer have to write code to build an AI model. We just have to prompt ChatGPT with a few sentences in English. So in the next few slides, I will review some examples of the application of AI in medicine. So AI has been applied to a wide range of clinical applications. Some common uses include clinical decision support for disease diagnosis, patient prognosis prediction, and for providing treatment recommendations. It has also been successfully applied in molecular subtyping of diseases and drug discovery or repurposing. So this list is by no means comprehensive, and I won't have time to review all the different uses of AI in medicine, but I will highlight a few examples. So a number of AI-based diagnostic tools have been developed, especially in radiology. This is the first RCT to investigate uses of AI in mammography screening. This study was published just a few weeks ago. The study showed that AI detected breast cancer as effectively as experienced radiologists, and it reduced workload by 44%. Here is another study that applied AI to automate classification of skin lesions and to diagnose malignancies. The model achieved performance with a level of competence comparable to dermatologists. So this is the first autonomous AI diagnostic tool and one of the few AI tools approved by the FDA in 2018. The system uses deep learning algorithm to analyze retinal images for diabetic retinopathy screening. So this technology has enabled screening for diabetic retinopathy in settings whereby patients do not have access to eye specialists. So AI models have also been applied to drive discovery of disease subtypes. This is a study that my colleagues and I conducted where we applied machine learning to identify clinical phenotypes in pediatric pulmonary hypertension. So pulmonary hypertension is classified into different subtypes based on the underlying pathophysiology. The motivation behind using an AI approach is that we can potentially produce a stratification that better reflects the range of clinical phenotypes. So in this analysis, we modeled the comorbidity patterns of pulmonary hypertension captured in clinical data, and we were able to identify clinically informative subtypes, including known PH subtypes shown here, as well as rare and under-recognized subtypes. So one of these rare subtypes that we detected was specific to systemic juvenile idiopathic arthritis, or JIA. Patients in this particular cluster had JIA and macrophage activation syndrome. And of course, we now know that pulmonary hypertension is a complication of systemic JIA. This subtype is rare and demonstrates the ability of the approach to discover rare disease subtypes. In this analysis, we applied a machine learning method known as Bayesian network. The advantage of this method is that unlike most other machine learning methods, Bayesian network produces an interpretable model as opposed to a black box, as in deep learning. So here is another study that explored the use of AI for disease classification. The goal here was to stratify patients with JIA into clinically distinct subgroups. The study applied an unsupervised machine learning approach and identified 5 subgroups with significant differences in a number of variables, including levels of pro-inflammatory cytokines, disease activity, demographics, and other clinical variables. Importantly, the machine learning derived subgroups appeared to stratify patients better than the classification system that is currently in use, which is the ILAR subtypes. As shown here in these graphs, differences across the subgroups had lower p-values than in the ILAR subtypes for both clinical and biologic variables. This points to the potential of using machine learning to inform a biologically based classification of disease. Here is another study that uses machine learning. They developed a predictive model to discriminate patients with juvenile onset SLE and healthy controls using immunophenotype data. The model was able to predict SLE with an AUC of 0.91, which is pretty impressive. So this graph shows the key contributing features used by the algorithm that discriminate SLE from healthy controls. At the top of the list were CD19 unswitched memory B cell and naive B cells. We can think of these as the immune signature of SLE identified by the algorithm. The study also applied cluster analysis to stratify patients based on their immunological signature. The analysis found 4 distinct subgroups with significant differences in T cell subsets. These immunological signatures can potentially allow us to target specific pathways in the treatment of these patients. So all the examples I've presented so far applied traditional AI. Here is an example of how generative AI is being used in medicine. In this study, generative AI techniques were used to synthesize CT scan slices of COVID-19 pneumonia. So at the onset of the pandemic, there was a lack of available COVID-19 images, which was a major barrier to developing tools to recognize the condition. Privacy concerns also limited the ability to share real patient images. And synthetic images generated by AI models allow researchers to overcome this data sharing bottleneck. And you can imagine that this technique can be useful in many other domains, especially in rare disease screening, for which few example images have been collected. Synthetic images can be used as a substitute for real image datasets to facilitate the development of imaging algorithms. There is also a growing effort to apply large language model methods to develop protein language models. So proteins can be represented as a language made up of amino acids. In the same way that words are strung together to form text sentences, amino acids are strung together to make proteins. And instead of training LLMs with vast volumes of text, protein language models are trained on tens of millions of protein sequences. LLM techniques have shown great promise in learning unobserved patterns from amino acid sequences that relate to their structure and function. So here is an example of how protein language model is being used. In this study, a model was trained to learn the evolution of IgG antibodies against COVID-19, Ebola, and influenza. Given a single starting sequence, the model generates plausible amino acid substitutions that were then experimentally screened for improved fitness. The study showed that a high proportion of the model suggestions boosted the ability of antibodies against COVID-19, Ebola, and influenza. This method has the potential to speed up development of antibody drugs, especially for targets that have resisted conventional design approaches. In another study, the same concept was applied to predict the genetic evolution of influenza virus. This model generated sequences that contained mutations identified within global influenza virus population for 73% of parent sequences. It also generated mutations at sites known for mutations for 78% of parent sequences. So the ability to predict the evolution of a pathogen has the potential to improve our ability to control, prevent, and treat diseases. So there is also a growing effort to develop clinical language models, which are LLMs specialized in clinical and biomedical text. So these are models trained on clinical and biomedical texts, such as clinical notes and scientific publications. The models can then be used to perform various clinical tasks, such as extracting information from clinical notes, medical question answering, and summarizing medical dialogues. So researchers have found that clinical language models outperform traditional machine learning models. They also require less labeled data and is therefore less costly to build. And importantly, they offer a user-friendly interface for human AI interactions. You can interact with the system the same way you interact with ChatGPT. Why would we need clinical language models when we can use ChatGPT? This is because specialized clinical language models almost always outperform general purpose models such as ChatGPT. So in the next few slides, I will briefly discuss the potential barriers to the use of AI in healthcare. I believe that one of the most critical barriers is that most AI models are complex. They're not transparent and can be challenging to interpret and explain. This applies to all models built using neural nets and deep learning. And as a result, we don't really know why a model behaves a certain way. And so it's difficult to assess how generalizable a model is and whether it introduces biases towards certain groups. And because we can't explain the model, it can be difficult to trust the model and to use it for clinical decision making. And importantly, we also don't know how to fix problems when they arise. For example, in ChatGPT, we don't know which of its billions of parameters need tweaking when the model makes a mistake. And because of this, concerns about patient safety and litigation will likely slow the acceptance of AI in healthcare, especially its use in diagnosis and treatment plans. Patients' distrust in AI models is also a potential barrier. A recent survey explored public views on AI in medicine. The survey found that there was significant discomfort among Americans with the idea of AI being used in their own healthcare. 6 in 10 US adults said they would feel uncomfortable if their own healthcare provider relied on AI. A majority of the public is unconvinced that the use of AI in health would actually improve health outcomes. So I'll give a few examples of how things can go wrong. In the beginning of my talk, I mentioned that ChatGPT was able to pass medical exams. We decided to do a test run. Dr. Mark Natter has kindly volunteered to run the test. One of the conversations went like this. Mark, which TNF inhibitor has the highest incidence of adverse effects? ChatGPT. According to a systematic review and meta-analysis of randomized controlled trials, infliximab had the highest incidence of serious adverse events. The incidence of malignancies range from 0 to 1.4 per 100 patient years for infliximab. This all sounds very convincing, except that it is not true. The incidence of malignancies is much lower than that. And also the citation provided here does not exist. So Mark asked ChatGPT, I cannot find this reference. Please provide a PubMed ID. ChatGPT replied, an error occurred. If this issue persists, please contact us through our help center. You can see that this is problematic if patients rely on ChatGPT for medical advice, and worse still if healthcare providers rely on ChatGPT for advice. AI systems can also be biased if the data they are trained on are biased, and even minor biases can be amplified by an AI system with far-reaching consequences. For example, in a report released by the Gender Shades Project, it was shown that state-of-the-art facial recognition technologies perform worse on darker-skinned females than lighter-skinned males, with an error rate of up to 34%. Another study showed disparities in the performance of AI algorithms in triaging skin diseases and identifying malignancies. This is partly because the AI models have not been trained on images of diverse skin tones. The study also found that dermatologists who often label AI datasets also perform worse on images of dark skin tones. And fine-tuning the models closed the performance gaps between light and dark skin tones. So this highlights the importance of ensuring the quality and diversity of data used for training AI models. Published data have also shown that text-to-image models have a tendency to amplify stereotypes about race and gender. Analysis of Stable Diffusion, which is an open source text-to-image software, showed that images generated for every high-paying job were dominated by males with lighter skin tones. For example, lawyer, politician, doctor, CEO, judge. And females with darker skin tones were more commonly generated by prompts for lower paying jobs, such as cashier, teacher, social worker. Use of such technology can perpetuate biases and discrimination with potentially wide implications for society. When AI fails in safety-critical tasks, the consequences can be dire. Self-driving cars have been involved in many accidents. And the first pedestrian death caused by self-driving car involved an Uber driver who struck a pedestrian while she was walking her bike across the street. So there were many contributing factors, but the most glaring mistakes were software-related. Uber's system was not equipped to identify or deal with pedestrians walking outside of a crosswalk. The algorithm was only trained to recognize pedestrians when they use a crosswalk. And so in safety-critical tasks, minor errors in the way we train an algorithm can pose serious threats. So a lot of work is now being done to make AI more reliable for use in healthcare. I strongly believe that to develop clinical AI technologies, partnership with domain experts is critical. AI models need to be informed by domain knowledge to help guard against spurious behaviors. And unfortunately, most AI models are developed by data scientists who have limited clinical domain knowledge. So this is an area that we're actively trying to address. We recently received funding from Pcori to develop an expert-guided machine learning approach to predict disease trajectories. We will be developing a machine learning approach that integrates clinical data, domain knowledge, and patients' lived experience to define the predictive models. The approach involves both clinicians and patient partners. We believe that this approach will not only make the models more relevant and reliable, but will also help build trust in AI models among clinicians and patients. Historically, clinicians and patients are not involved in the development of AI models. I believe that given the highly disruptive potential of these technologies, the medical community can no longer afford to be on the sideline, and the medical community needs to be actively involved in shaping the creation of AI technologies in medicine. So in the next few slides, I will briefly describe the potential threats of AI. One of the topmost concerns is, what does this mean for jobs and skills? AI is expected to eliminate the need for up to 30% of certain jobs while creating new ones. It could give rise to new opportunities, but there will be instability for displaced workers. This is a serious concern given that automation has been a significant driver of income inequality globally. So in healthcare, many consider radiology to be a clear case of a highly skilled white-collar occupation facing serious competition from AI. Numerous studies have shown that automated image interpretation is just as good as radiologists. And in 2016, a paper in a leading radiology journal stated that machine learning will become a powerful source in radiology in the next 5 to 10 years. And indeed, in a few years, there may be no specialty called radiology. This view was echoed by Geoffrey Hinton, who was considered the father of deep AI, modern AI. In a speech he gave in 2016, he said this: "If you work as a radiologist, you're like the coyote that is already over the edge of the cliff, but hasn't yet looked down, so doesn't realize that there is no ground underneath him. People should stop training radiologists now. It's just completely obvious within 5 years, deep learning is going to do better. So those projections were made 7 years ago. Where are we today? This study looked at actual job loss in selected occupations considered at risk from automation, including healthcare providers, retail salespersons, administrative assistants, and so on. The study showed that so far, there is no clear evidence that AI is causing job loss at any scale. There are occupations that did decline, but they were mostly due to previous waves of computing technology and other trends such as offshoring rather than automation due to AI. The study also specifically looked at the field of radiology and showed that the field has not declined. In fact, the number of radiologists whose main activity was patient care has increased and is projected to continue to grow. The workload of individual radiologists has also increased substantially over the past decade due to the increased use of imaging. So clearly, predictions of rapid labor substitution by AI are unlikely to be realized. This study predates ChatGPT. Whether these trends will persist remain unknown. So different people have different views on how impactful generative AI will really be. Personally, I strongly doubt that AI will be performing medical miracles anytime soon, but it may help ease the burden of more mundane tasks, such as report creation and administrative paperwork required for billing purposes. And these will be very important contributions. So I believe the same applies to other industries, whereby AI will augment rather than replace jobs. This ad on a construction site in Belgium was meant to be a swipe at the hype around ChatGPT. It says, "Hey, ChatGPT, finish this building. Your skills are irreplaceable." AI won't be building a high-rise anytime soon, but it may change the way we build buildings. It may change how quickly projects are finished. And the likeliest outcome of the current AI revolution is what has pretty much always happened when humans acquire new technologies. The technology augments our capabilities rather than replaces us. So some of you may have heard of the Gartner hype curve, which describes the maturity and adoption of emerging technologies over time. A typical cycle begins with an innovation trigger and a rise in expectations about the potential of a technology. At the peak of inflated expectations, the technology's popularity and hype reach their peak. But practical limitations of a technology start to become apparent. And so this leads to a sense of disillusionment, and the hype begins to wane, leading to a trough of disillusionment. And in the slope of enlightenment, the technology starts to find most practical and realistic applications. The understanding of how to use the technology also begins to increase. Many of us believe that generative AI and ChatGPT are at the peak of inflated expectations right now. In fact, there is evidence showing that interest in ChatGPT may have waned. The number of people visiting ChatGPT's website and downloading this app fell for the first time in July. So coming back to the question, will AI replace doctors? I personally don't think so. AI has made significant inroads, but is far from being able to diagnose or treat patients, and it certainly cannot replace compassionate care. But physicians who use AI will most likely replace physicians who don't. So here are some recommended papers on the subject that you might find helpful. To conclude, generative AI and ChatGPT are no doubt an impressive technological achievement. And if used correctly and responsibly, it can potentially help improve healthcare delivery. But its adoption in healthcare needs to be tempered by an understanding of its limitations and potential risk. And I hope that this presentation has given you some insights into that. So thank you again for having me I'll be happy to take any questions.
All right. Thank you so much, Dr. Ong. Please use the Q&A feature here of Zoom, and I'll try to moderate this. Dr. Hennigan has a question. One challenge in the development and validation of machine learning algorithms is the need for large amounts of data. In pediatrics, where almost all of the patients we see have rare diseases compared to adult medicine, how can we overcome this?
So the promise of generative AI technology and large language models, they can pre-train models using other data sources. And then you can build on these pre-trained models with fewer samples to train your machine learning model. So it has been shown that this method works for a number of rare diseases. They call it one-shot learning, where you can learn to predict an outcome with fewer samples when you use a pre-trained model. Does that make sense? I'll be happy to share some references on that subject if that is of interest.
Yeah, thanks.
So Bryce,
Yes.
yeah,
Go
I
ahead,
had a
Joe.
question, but I can't access the Q&A.
Oh,
How does AI deal with the challenge of quality of data? I mean, we all see, studies that are borderline good methodologically that sometimes go off and inform practice and send people down the wrong track. How does AI distinguish that and distinguish timeliness? So, it's based on historical experience, but we're looking at things trying to move them forward.
So AI models don't actually check for the quality of the data. It is up to the people who train the AI models to ensure that the quality of data are adequate. This is one of the problems with many AI models. You find that they train on a particular data set, but they're not generalizable because the data just isn't good enough, isn't generalizable enough. And oftentimes you don't know that until you try it out in another setting.
Thank you.
Does that answer your question?
Yeah, that helps a bunch.
there's a very specific question here in the chat. Can you briefly explain the difference between ChatGPT 3.5 versus 4.0?
So ChatGPT 4.0 is a more recent version of ChatGPT and a much improved version of ChatGPT. Does that answer your question?
And so there's a follow-up from the same person who says, last week, Epic mentioned that they will be integrating the 4.0 version into the EMR, including scribing capabilities. How do you think it will be HIPAA compliant? Privacy concerns.
That's interesting. If they're sending information across the internet, which we do with ChatGPT 4, then it will not be HIPAA compliant. Unless they're building their own system, they have their internal model that they've built, it will not be HIPAA compliant.
Interesting. I have a sort of more general question in terms of how AI may affect medical education. So obviously, medicine know what it is to be starting out in medical school and acquiring knowledge and becoming more refined in how we apply that knowledge and pattern recognition and so forth. With AI, the pattern recognition is sort of built into it. That's the main feature of it. So how do you envision this interacting with medical education or changing medical education, the way doctors become doctors?
I think AI can be a useful tool in education, but bear in mind that it is only trained to predict the next word, and it does a good job at that, but it's only trained using the data on the internet or whatever data you use to train it. And if the data is not up to date, you will not have knowledge that is up to date. And even if it is up to date, its job is to predict the next word. It will not always give you a logical or consistent or correct answer. So my thinking is that it can be a useful tool, but it cannot replace traditional education.
And the sort of you keep mentioning that the quality of the input really dictates the quality of the output, garbage in, garbage out, and vice versa.
Right.
And so are there automated ways? I would presume there are automated ways to keep refreshing the input such that the algorithms have the most recent data. Is that built into the systems, or do they have to be sort of manually prompted to update? Like, do you understand what I'm asking?
Yeah. So that is the best practice approach, that we should always continue to update AI models, but they're very expensive to do so, especially for large models. I think ChatGPT costs millions of dollars to train. So depending on the size of the model, it could be very costly to do. But there's now, so NQF is now forming a committee to try and understand how we can better improve the quality of AI using quality measures that we normally use in healthcare delivery. So one of the methods that has been proposed is to have a surveillance of key indicators. If there are deviations in those indicators, then it might be time to retrain your AI models. Does that answer your question?
Yes, thank you. There's a new question here also. How do you suggest doctors best learn to use AI? Are there sources other than ChatGPT we should be familiar with?
There are clinical language models. Some models there are a few pre-trained clinical language models that are trained using clinical notes and publications. Those might be more accurate in terms of medical knowledge. There are open source applications out there that physicians can use too. Again, I'll be happy to send references. Feel free to shoot me an email.
Let's see, a couple others here. Have you seen any research or example for AI usage to aid access to healthcare in resource denied settings? I suppose we would have to rely on internet access in those areas too.
I think there are efforts to make AI more equitable, especially in low resource areas, but I'm not aware of specific studies. I'm sorry.
All right. And then I have another question which relates to sort of AI generated information. So there are examples of I don't know whether it was ChatGPT or another, generating an entire scientific publication. And I heard on NPR this morning about AI generated music that's hard to differentiate from that of an original artist. And so what are the best ways to detect that sort of thing? And what are obviously there are potential pitfalls with AI generated material that appears to be an original work. Maybe it isn't considered an original work, but not from a human mind. And so are there best practices about how to detect that and so forth?
People have tried to come up with best practices, for example, to detect fake images. Most AI generated images, they don't tend to render fingers very well, or they have different color earrings and little mistakes like that you can spot. But the problem with that is AI models are getting better at generating fake photos. So now people are scrambling, trying to understand how to differentiate fake versus real photos. And I saw an article in the Post just yesterday that Google has introduced a watermark that is not visible to users, but it's there, and you can detect in fake images generated by AI. So there are multiple efforts going on to address this problem, but right now we don't have a good solution, unfortunately.
All right. Other questions from the audience or panelists here? No? All right. If not, Dr. Ong, thank you again so much for an enlightening talk, and looking forward to seeing how this goes forward in the future. It's an exciting time. And
Thanks very much for
really
having
appreciate
me.
you joining us from Sydney and staying up late to give grand rounds today. Thank you.
Very great
Thank you very much.
presentation. Thank you very
Thank you.
much.
Thank you. Bye-bye.
Bye.